Okay. So I think we pretty much covered all the important basics for the simple fully connected neural network and later the convolutional neural networks. So next, I want to talk about the interpretation of the deep neural networks, which I think is a very important aspect for a lot of applications, especially in medical image computing. Right, interpretation is very important, right? Because we want to understand, right, how the machine learning model is making the decision, right? Why making this decision, and this can help the physicians or doctors to understand, right, if something is going to be concur with the expert knowledge, or maybe there's something the AI may not do a good job, right? So the physicians can make the correction. Okay. So here is a list. I think this symposium on this interpretable machine learning. So I think there's like a panel for the debate, right? If the interpretability is necessary. So if you're interested, you can check out this YouTube video. And but in a lot of applications, especially using AI or machine learning as a service, right? Either commercial or maybe in the healthcare or medical domain, right? The interpretability is a necessary component, as I mentioned, right? We need to provide some of the reasoning or explanation, right? Why machine learning makes such a decision. If there's an error, right? How can we understand the error and make necessary, revision to the model, or constantly improving the model over time. So the simplest way we can explain or provide some interpretability of the deep neural networks is to visualize the filters, right? So when we talk about CNN, I also show you this kind of visualization, right? We can actually plot these filters or kernels in each layer and try to visualize it, right? So here, this is the AlexNet, ResNet, right? Different type of neural network architecture, and they're learned filters by training on the ImageNet. Okay, so these are the visualization of the initial layers, the first layer, right? So you can see that although they are different network architectures, right? But they learn very similar patterns, right? Mostly different edges, right? Different color component. Okay, so we can get a sense, right? All these networks are actually learning from the data. Okay, maybe let me get rid of this first. Okay, see if I can minimize this. Okay, anyway. Okay, so, okay, there we go. In this slide, right, so this basically show more layers, right? Layer 2 and layer 3. Of course, maybe you cannot visualize all the different weights of filters, right? Because, we can specify like hundreds of learnable filters in each of the layer. But maybe you can selectively, show or plot some of the filters and get a sense, right? What different layers they are actually, learning from the data. But this gives you some very basic or vague idea, but does not provide very informative, information, right? So you see a bunch of patterns, but still you are not quite sure, right? What exactly going on, right? Why do this network make the final such decision? So at the end, we can also show the last layer, right? So this is the fully connect layer. If we're doing the classification or any other task, right? So these are the most important layer, right? Because later we'll connect the softmax and make the prediction, right? So these are the high-level representation, that is going to be extracted from the previous layer. So here made a example is that this fully connect layer has the 4096 dimensional feature vector, right? So these are the feature vectors going to be immediately used for classification, right? So we want to understand, right, how good is this, feature vector for classification, right? Are they discriminative enough to distinguish, among different classes, right? So how do we examine these feature vectors, right? I mean, for one thing is you can plot, right? You can treat it as a feature vector, then you can plot it, but that won't give you much information, right? Because these are just a bunch of numbers and you plot it, it's just like a different curves, right? So it doesn't give you whole lot of information. So here, what we can do is we can actually run this network, on different images, right? We can run this network on the training images, right? And for each of the images, we can get a corresponding last layer feature vector, right? Those 4096 dimensional feature vector, right? So each one we have a corresponding feature vector, okay? And we can also do this, right, for the test image, right? So because we are using the same model, right? We can also get the corresponding feature vector for each of the test image. And then we can using for one particular test image, right? Let's say we consider, I'm still using the pen here, okay? So let's just consider this flower image, right? So we get this feature vector, and let's assuming we run this CNN on all the images in the training set. So each of the training images, we have a corresponding last layer feature vector, right? So then we can do this nearest neighbor search, right? So based on the feature vector, we can find the k nearest neighbor in the training data set from the training database, okay? So in this case, let's consider the top, 6 nearest neighbor, okay? And once we found those 6 nearest neighbor in the feature space, we can find this corresponding original image, right? So these are the images and corresponding to that is the top closest neighbor with this test image. And we can do another image like this, right? So we get this, top 6 nearest neighbor as this. So we can do this and kind of examine, right, if these feature is meaningful or is actually makes sense, right? So, but from these example, we can actually form a conclusion, right? These feature representation are actually very good, right? So for each of the test image, the retrieved images in the training database is actually corresponding to the same class, right? So they all corresponding to maybe this flower class or specific type of flower, right? If you look at this, the color all have this kind of purplish color, right? So this here, the elephant, the retrieved image all contain the elephant as an object in the image, right? So here, maybe there's a ship on the sea, right? So we all retrieved image has the similar object. So in a way, you kind of get some idea, right? So these are the feature very meaningful, which means the model learns some useful information. As a comparison, right, if we don't consider these features, right, extracted by the network, if we just directly using the original image and using that, like the pixel intensity as the feature to do the nearest neighbor retrieval, and we can see what we got here, right? So I think this is a boat in this image, right? But if you look at this retrieved 6 nearest neighbor, right? So they don't belong to the same class as boat, right? So here clearly there's a white horse, right? So this is clearly a wrong class, but it kind of understandable, right? Because we are only using the pixel intensity to retrieve the nearest neighbor, right? So here happens this object also contain the white color, right, white horse, and has the dark background, right? So these pixel intensity are very similar or close to the query image. So that's why this will be retrieved as a close neighbor. So similarly, you can find other examples, right? They not belong to the same class, but bear some similarities in terms of pixel intensity. So this is not a good choice to do the classification. But here in the feature space, we can determine, right? So the learned representations are actually meaningful. Okay, so this is another way you can kind of explain or interpret what exactly the network is learning from the data. Okay, so in the previous example, we use a nearest neighbor retrieval, right? So, but you may feel like, okay, that kind of is a little bit complex, right? I have to extract the feature and do the nearest neighbor retrieval. Is there a more efficient way I can, get some information from the feature? So here actually is another maybe simpler way to do is we can just visualize the feature representation, right? Maybe 4096 dimensional vector is too large. What we can do is we can use some of the dimensionality reduction algorithm or method, like a principal component analysis, right, to reduce the dimensionality into maybe 2D or 3D space so that we can plot and visualize, right, how they distributed across the space, right? So here I'm showing this, 2D visualization, right? So we can compress these high dimensional feature vector into a 2D space, 2-dimension. So in this case, we can actually plot them, okay? So you may not able to see the details, but actually these are just, plot. This is due to the MNIST digit classification. So we can plot these feature vectors, and actually you can see, different digits, they actually cluster within a tight cluster. Okay, so these different clusters are actually corresponding to a different digit. So you get a sense, right? The feature representation actually doing good job to extract some discriminant information so that different digits can be separated, right? And there's also more advanced, technique called the TSNE. So also very commonly used to do this kind of visualization. You reduce the feature vector from high dimensional space into a low dimensional space, then you can do the visualization. So I also recommend you check out TSNE. So here's the reference. You can check it out. And also, the code, everything is available. So basically in the machine learning toolbox, you can easily call this function and get the visualization. Okay, so that's another way you can do some interpretation of the network. Okay, so far we introduced a couple of ways, right? You can more or less get a sense, right, what this network is learning, or some of the learned representation is meaningful or not. But still, we are still not able to explain, right, why the network makes such decision, right? For example, in this slides here, right? So this is an input image, right? Go through this network and make a decision called, the network predict. This is a cafeteria image, right? So, I mean, we can visualize these images, the feature vectors using the previous method, right? And see if it does make some meaningful representation, but it's still not clear why the network, determine this as cafeteria, right? What kind of information the network is actually used to make this decision, right? As a human, right? If we examine this image, we can tell this is a cafeteria or restaurant by looking at or trying to find some informative or attribute in this image, right? Maybe we pay attention to or trying to find if there's like a cafeteria-like feature, right? There's a table, maybe some of the plate or utensils or people sitting around eating dishes, etc. Right? So these are the information for human. If we want to make a decision, those are the attributes or information we try to find from the image, right? But how does this network, make decision? What kind of information the network is used to make such decision? So we want to understand from this perspective, right? So in this work, right? So the reference list here, they trying to answer this question, right? Why the network is making this decision? Why, based on what? Based on what information, right? So in this example, actually, they are able to kind of highlight the region or the pixels, actually, to explain like why this network make a prediction. For example, here, right? So this network make a prediction. This is a conference center, okay? And if you look at, right, so this example, actually, there's a heat map, right, overlay on the original input image, right? You see this kind of reddish, yellowish color, right? So that's called the heat map. Basically, kind of highlight the region, right? So the more red color indicating, these pixels are more important for the network to make a prediction. So we can see that actually these are a very good explanation, right? So the heat map shows for the network to make a prediction as a conference center, actually they focus on these particular region, right? The red color highlighted region, right? There's a microphone, maybe there's a podium, and this person was standing here, and there's another person standing there, also holding a microphone, trying to maybe ask a question or maybe trying to discuss with these presenter, right? So these are the information this network highly rely on to predict this is a conference center. If we switch to another example here, right, on the right, the network predict this is an indoor booth, right? So let's see what region, this network specifically pay attention to, right? So we again look at the heat map where, the most highlighted region is indicating by this red color. So you can see that the highlighted region corresponding to this kind of poster region, right? There's a poster and there's a crowd of people, standing in front of this poster, right? Maybe listen to the presenter or asking question there. So this kind of help the network to determine this is an indoor booth, right? So, for booths, you usually have something like a table, or maybe there's a poster to presenting something, right? So it's kind of give you some reasonable explanation, right? Why the network make such a decision, okay? So that's kind of give you an example, right? What this method can do, trying to highlight the important regions that the network is focused on to make the prediction. But let's see how the method is actually able to achieve or get this kind of attention map, right, or heat map to highlight the most important region. Right. So what they do is here you have an input image, right? You have a standard CNN with a couple of convolutional layers, and at the end you have a global average pooling. Okay. So we talk about the pooling layer, right? So we know we have the max pooling or average pooling, right? So this global average pooling is that, we treat this entire feature map like a cell, okay? And we just, pull a single value, right? Take the average of this entire feature map and get a value, okay? So in this case, each of the feature map, if you do the global pool, you get a value, a single value, okay? And after this global average pooling, you will get another layer. This is a simple logistic layer, right? You're adding a couple of weights and you give out a class probability, okay? So if we look at this, look at the global average pooling and also this logistic layer, right? Adding the weights to generate the prediction. this output probability is actually proportional to this global average put feature and the weights, right? So we can write in this kind of two summations multiply, right? This global average put feature multiply with these weights, right? So, and because of this, inner order summation correlation, we can reorganize these equation like this. And this happens to be a weighted sum, right, of all these feature map, right? So this FKHW, right, and multiply with this WC, WKC is actually the weights, right, for this logistic layer, right, the last layer before the classification output. Okay, so if we let's say this example, right, give the largest class probability to the class of dog, right, which is 0.8, right? So here we can backtrace, right? So let's say, why does this network give a highest probability to the dog class? We want to backtrace it and see what's the pixel value this network actually focused on, right? So we can, using this technique, and generate this weighted sum or weighted average of this feature map, right? So this is the final weighted average feature map, and the author called this class activation map, right? So which class, for which kind of class this the region has been mostly activated, right? So these are the highlighted region. If we go to the original image, right, which is here, it kind of highlight the pixel, right, of the dog, right? So that's why you see there's the highest probability for this dog, because the network mostly focus on the pixels of the dog. Okay. You can also change to another class, right? So maybe I want to see other classes, right? Let's say here we have a cat class, right? And this network give a probability maybe equals to 0.1, right? We can do the same, right? Here we can connect with the weights, connect to the cat class, right? Not this W1, 2, and Wn, right? So that's why we have a class superscript C here, right? So we have the which type of classes, maybe K, okay? So which classes it belongs to, right? So we can have another set of weights here, and we can generate another class activation map that is specifically belong to the category of cat, right? Maybe in this case, we don't actually have a cat object in this image. Maybe the class activation map will be maybe some random places, right? Maybe if there's another class called people or human, right? Maybe this network will highlight these regions, right? Because we do have a human object, right, in this image. Okay, so that's the basic idea, right, of doing this kind of classification, class activation map, trying to identify, right, which pixels or regions this network is focused on, and make a prediction. Okay. So here we can see more example, right? So this paper, they're using this class activation map to explain the prediction of deep neural networks. So here are the this particular input, and these are the top three predictions, right? So these are the top three predictions according to the output probability. Okay, so dome has the highest, the second is the palace, and the third is church. So if we for a individual class, right, we can generate the corresponding class activation map, and this is where the network is focused on by making prediction of dome, right? So mostly focused on like the roof or dome region. And if the making prediction of palace, right? So here maybe focus on the bottom section, right? The building section. Okay. And if make a prediction of church, right? So they look at actually both, right? Maybe in a lot of examples, right? Church may have similar structure like this, or both of them are important. So here is like a collection of different input, and actually this is like a videos, and you can see the network generate different predictions, right? And also highlight the region, right? The red color indicating or focus region is the most important region to make the corresponding prediction. Okay, so I think you get some basic idea, right? So for different classes, right, these attention map are kind of different, right? Which part this network is focused on to make a prediction. So I don't know if you noticed, there are a couple of very interesting example, right? Specifically, there's a couple of making a prediction of prison, right? So maybe I can go from the beginning. Yeah, this is another example of making prediction of prison. Maybe it's because of this, maybe the vertical or maybe some of the patterns, maybe bear some similarity as the prison bars, right? So actually in the very beginning, right, in the alley, there's like a, trash, those dumpsters or trash cans there, those metal, they have those vertical bars there. So that kind of make the network think maybe that's the prison bar to make that prediction. So for us, we can definitely tell, right? We will never make this a prediction. This is a prison, but for this kind of explanation, we get idea, right? Why the network make such a prediction, right? Because it is relying on a certain features, right? These vertical bars or line patterns to make a prediction. So here, this is a golf cart, right? So also you kind of get idea, right? Why this network will make a prediction like a golf cart, right? Okay. So in addition to using this kind of method, trying to get a sense, right, why the network is make such prediction, we can also using this technique to explain some of the failure cases, right? When the network make a false prediction, we can also look at what regions the network is actually focused on, so that will cause the false prediction. So for this example, right? So the ground truth is actually house, but the prediction from the network is called sushi bar. Okay. And this is the class activation map. And we can see here, right, this sushi bar actually have the highest probability. And this is the corresponding regions the network is focused on to make a prediction of sushi bar. So actually focus on, like, there's a bar here, then there's people behind it, right? There's a kitchen sink. In the database, a lot of sushi bar example, right? You often see people behind the bar and making the sushi, right? So that's why, this network, by learning from those examples, they learned such patterns. Then, you trying to identify or trying to find such patterns so that make a prediction of sushi bar. And here's another example, right? So I think the ground truth is probably apartment, but this prediction is called martial arts gym, right? Interestingly, you can see how the network, based on what, make such a decision, right? So you kind of focus on this bare foot of this person, right? So in a lot of martial arts gym, right, people do like a barefoot doing some karate or maybe other sports. So that's very interesting that, right, to see that the network will try to find this kind of patterns and make a prediction. Okay, but again, we are not just trying to see why the network makes such false prediction. And this kind of explanation may also help us, right? How can we improve the model, right? Maybe the model here is learning some biased information, right? Or or maybe this example is too, maybe too complex or too difficult, right? So we can actually design some mechanism, trying to correct or debias the model, right? Maybe focus on other things, trying to, make the accurate prediction. So this could also help us, right, to get some idea or get some insight, what kind of aspect we can try to improve the robustness or the performance of the model. Okay. For this work, doing this kind of highlighting the region, actually the author also using this to do the weakly supervised localization. Okay, so for localization or object detection, right? So if we are doing this in a fully supervised way, what we need is in the training stage, right? If we're doing object detection or object localization, right? So we need to have this ground truth label, which is the bounding box, right? So we need the annotation to train the model. You have an object and we have a corresponding box label. You can train localization in a fully supervised way. But here, since this network is trained using image classification, right? In the training data, we don't know the location, right? We don't have the bounding box annotation. All we know is the image level label, right? We know this is a starfish image, right? Which means there is a starfish somewhere, but we don't provide a specific bounding box annotation for that object. But because of this class activation map is able to highlight, right? If we make a prediction of starfish, so these heat map or class activation map is actually able to highlight the pixels or the regions, right? Give this prediction of starfish. Then we can actually leverage this information to localize, right? So basically what we can do is, this is a heat map, right? Have the value between 0 and 1, 1 being close to the red. What we can do is we can set up a threshold, right? Maybe let's say we can set a threshold to 0.6 or 7, right? In this case, we can generate a binary mask based on this heat map, right? And then we can using the mask to generate a corresponding bounding box and using that as a localization, right? So the author using this kind of interesting mechanism and to do the weakly supervised localization, right? So the supervision is called weakly supervised because we only have image level. It's not like a fine-grained supervision. It's a very coarse supervision, a very weak supervision, right? The strong supervision will be the actual ground truth bounding box. So in this case, they did this method and evaluate the localization accuracy. They were able to achieve 62.9 localization accuracy. But if you look at this fully supervision, right? If we're using the actual ground truth bounding box and train the network to do the localization, it is able to achieve a 65.8. So the gap is not very large, right? But this weakly supervision has the advantage of saving you a lot of annotation effort, right? Because we only need to know the image level. We don't have to provide very accurate bounding box annotation. So that's a big advantage in terms of the labeling process. Okay, so here is another example of prediction the tricycle, and based on the activation map, we are able to localize where that tricycle is in this particular image. Okay. So that's the mechanism of class activation map and how it can be used, not just for interpretation of the deep neural network, but you can also use that to do the object localization. But one limitation of using the CAM is that any CM-based network must change its architecture, because there's a necessary component called global average pooling, right? So they're using the global average pooling to get a single value and multiply with that, the later logistic layer, right? The weights. So for any of the network, if you want to use in CAM, then you have to modify the network to have the global average pooling, okay? So to address this limitation, the later work called gradient CAM, trying to address this limitation and propose this kind of gradient weighted class activation map so that you don't have to require this architectural change. So basically you don't need global average pooling in your network, okay? And in this case, you don't have to retrain the model, to switch to GAP. You just have to use whatever the original network you are using, okay? So, and it also shows that it will give a more precise localization in their paper. So if you're interested, you can read more from this reference, gradient CAM paper. Here, I'll also show a couple of visualization, right? What this activation map, this gradient CAM is able to provide, right? So if we want to examine, right, the prediction of a cat, it actually highlight this cat region, okay? If we switch to another class as dog, and you can see that the class activation also change, right, to more focus on the face region of this dog, okay? So here they also did this weakly supervised localization, right? So they compare with CAM as well. So they are able to have a better result. So if you're interested, you can go to this paper and dive into some of the details. And another interesting thing they do in the gradient CAM paper is that they can also identify bias in the data set. Okay, so they provide a couple of examples to explain their observations. Okay, so in the first row, right, so we have the input, and this is the gradient CAM for the biased model. Okay, if the model is biased, right, this is the prediction of the model is nurse, and this is the gradient CAM highlighted region, right? So mostly highlight the face of the region, okay? And for the second row, this is for the third example, this is the unbiased model, right? Instead of looking at the face region, you look at the short sleeve. Still, I'm not sure if this is the correct patterns we should be looking for to predict this is a nurse, but definitely it's not that biased, right? Because if we look at the face, maybe they are looking for maybe this bias to like a female nurse in this database, but we also have male nurses as well, right? So we cannot base on the face to determine if it's a nurse or maybe other occupation. And on the second row, here's another example, right? So this bias model predict, right? This is a nurse, right? Again, they are focused on the face region, right? But for this unbiased model, right, is predict as a doctor, right? It does not, based on the biased information, does not rely on the face, but actually focus on some of the medical device, like in this example, actually focus on this stethoscope. Okay, so this is another observation they find, which maybe we can use in gradient CAM to identify the bias in the data set. And gradient CAM was also used a lot for medical image analysis, right? So for this example, they're using gradient CAM for glaucoma diagnosis and localization, right? So they can, again, this can be simply a classification task, right? To classify if there's a normal or there's a glaucoma, cases or images, right? Then we can using the gradient CAM activation map, to highlight the region, right? To make a prediction and trying to localize. Okay. So here are some of the reference. Of course, this visual explanation is a very important area. So there's also other follow-up work trying to even improve gradient CAM, right? So they have this gradient CAM++, and they also have other variants of gradient CAM. So more to trying to address some of the limitation of previous works. So I also encourage you to look into these references if you are interested, in this kind of different mechanism or how they improve the visual explanations. Okay, and all these different methods, they have this code available. So in your project or in your applications, if you're interested in doing some interpretation, by doing some visual explanation, you can using the code to do that. Okay.